Hello, I want us to explore the electrophilic aromatic substitution. So we are going to use the aromatic compound as a nucleophile to attack an electrophile. Okay, but the problem is aromatic compounds like benzene is stabilized by aromaticity, and therefore they are not able to undergo most of the reactions that we learned earlier. For example, if we try to do bromination using bromine alone, expecting to achieve that product, there's no reaction. So we need to transform the electrophile into a very good electrophile. Okay. So what we can do is to use the Lewis acid here, the aluminum tribromide. We can also use iron tribromide. That would also work. Okay. So the Lewis acid is going to interact with the bromine as a Lewis base to form a Lewis complex. In the Lewis complex, this bromine is now a good electrophile. So the ring can be able to do a nucleophilic attack to install the bromine in that position. And of course, in the process, it generates the cation. This cation is stabilized by resonance. So these three resonance structures, we call them the sigma complex. The sigma complex can be re-aromatized. So in the process, we generated this aluminum tetrabromide. So we can use this bonding pair to be able to do a proton transfer, okay, which re-aromatizes the compound to the expected product. And we regenerate the Lewis acid, and of course we also form the HBr in the solution. Okay. How about if we want to achieve sulfonation? Is there a way to get a good electrophile to achieve that reaction? Well, it happens that if we use concentrated sulfuric acid, which is fuming sulfuric acid, it contains sulfur trioxide. Okay, so the sulfur trioxide is a good electrophile which can be attacked by the benzene ring, and then we generate the sigma complex, and then the water is going to come and do a proton transfer to re-aromatize the compound, and then once we form the compound here, we can actually be able to protonate it to get the product. Okay, this reaction is actually reversible. So if we use dilute sulfuric acid, we can be able to get it back to the benzene. So it is one of the processes that can be utilized in protection, deprotection of these kind of reactions. Okay. What about if you want to achieve nitration? Is there a way to get a good electrophile from that? Well, what could happen is if we use nitric acid and sulfuric acid, the nitric acid is going to act as a base. So it's going to pick a proton from the sulfuric acid, which turns the hydroxyl group into a good leaving group. It turns it into water. And then we generate nitronium ion. Nitronium ion is stable enough and a very good electrophile. So therefore, the benzene ring is going to attack that. And then, of course, we have water there, which will help do the re-aromatization. So the exact processes that we have learned in the last two slides, that is, once you have a good electrophile, you generate the sigma complex, then you do re-aromatization to get the product. And if you want to get an amine, we can do nitration, and then we follow it with reduction, which we can achieve using a metal, like in the presence of an acid, to form the ammonium ion. The ammonium ion can be neutralized with sodium hydroxide to get the aniline in this case. Another reaction we could do is Friedel-Crafts alkylation. That is, we can install an alkyl group onto the benzene ring. Okay. So to do so, we can use an alkyl halide with the Lewis acid. So it's going to form a complex, and then the complex transforms into a carbocation, which is going to be stabilized by the charge that is from the aluminum tetrachloride. Okay, but the carbocation is going to undergo a rearrangement if there's a possibility to create a more stable carbocation. For example, assuming we wanted this one to be the major product, and so we need to start with the N-butyl chloride, it is going to undergo a rearrangement. So here, the likelihood is you are expecting to form a primary carbocation, which really doesn't form because it is highly unstable. So then this compound is going to undergo a hydride shift to generate a secondary carbocation. So we end up with the product being more substituted, which was not expected. If you want the one that is less substituted, then there's a problem. Okay, that cannot be achieved with Friedel-Crafts alkylation. What are some of the other major limitations of Friedel-Crafts alkylation that you can recall from the notes? Well, I mentioned in the notes that if we try to do Friedel-Crafts alkylation using a compound that is more that makes the ring more activated. So, for example, if we just install that first group onto the ring, then what happens is that the alkyl group is electron donating. So because it's electron donating, once you install the first one, it makes the ring more reactive. So you end up with what is called polyalkylation. So that means you're going to end up with the alkylation taking place in various positions. Okay? But there's a way to control that. What you could do is to use excess of the benzene, like you can use a ratio of 6 equivalent for every 1 equivalent of your alkyl group. Okay? For every 1 equivalent, you use 6 equivalent of the benzene ring. Then you can distill the benzene ring after the reaction and get it back. Okay, that is a way to solve it. But there are also other limitations that can be experienced with Friedel-Crafts alkylation. Okay, another one is that if there is a deactivating group on the ring and you want to do an alkylation, then Friedel-Crafts alkylation will not undergo a reaction because the ring is deactivated. Okay, in other words, the product is going to be negligible. The yield is going to be too low. If you have another strong deactivator like nitro group, there's going to be no reaction. Okay. If you do have a strong activating group like an amine or a hydroxyl, like you have a phenol, so you can have aniline or a phenol. Those are strong activating groups. So the problem is these compounds will also act as Lewis bases. So they are going to compete with the alkyl halide in the formation of Lewis complex. Then once you form the ammonium ion in this case, then that turns out to be a deactivating group. Because of the positive charge here, now it's going to be electron deficient. So it turns out that that kind of competition now makes the ring less reactive. So the use of amines is kind of limited and phenols when doing such kind of reactions. So how do we solve some of the problems? Well, we can use what is called Friedel-Crafts acylation. How does that work? We use an acid halide. This is called an acid halide. So the acid halide forms a complex with the Lewis acid. And then once it forms that complex, it generates the acylium ion. The acylium ion is resonance stabilized. So the benzene ring can attack the acylium ion, then it forms a sigma complex exactly in the same format we have learned in the previous slides. It forms a sigma complex, and then once it forms the sigma complex, then the aluminum tetrachloride in this case is going to help do the re-aromatization, and then we form the product. So the good thing with this reaction is that once you install the first one, the ring is kind of deactivated because you have an electron withdrawing group. So the ring is deactivated, so there is no polyalkylation. No rearrangement, no polyalkylation. Okay?